Yeah, so what, can you guys tell me about statistics? What are statistics?
Statistics is math with words, and it's the word.
Oh, what did I do? So this guy said that statistics, you know, Sir Francis Galton, statistics are the only tools by which an opening can be cut through the formidable thicket of difficulties that bars the path of those who pursue the science of man. I don't know about that. So, and then you've heard about the rule that there's 3 different kinds of lies. Yeah.
Lies, damn lies, and statistics.
How, oh, you got the damn thing. So, but what are statistics used for? And you see, you got the damn thing. That's why I don't post it. So I'm gonna ask you. Is this one in there too?
Statistics are used to weed out people that don't really want to do it. Statistics suck.
Not really. Statistics can be quite useful, and you'll see in the clinical lab, all your reference intervals are based on statistics, and all your quality control is based on statistics. So, but basically you have descriptive statistics, you know, that's used to characterize data. Can you give me some examples of some descriptors? Descriptors. You've heard of that term. Descriptors are what you use to describe things, right? Huh?
Yeah, we're probably getting ready. That's smart people words. Don't do those.
Descriptors. What's a descriptor? You can divide us up into descriptors. There's 1, 2, 3, 4, 5, 6 males and 1, 2. So male or female, that's a descriptor and other things. They're not non-quantitative. Statistical analysis is used to distinguish between random and meaningful variations. So we could go ahead and measure all of our heights, and that's going to be random variation, although there might be meaningful variation because we do have sexual dimorphism, right? So on average, the mean, that might be different populations between males and females, right? So that might be a meaningful variation. In the lab, we're going to use statistics to monitor and verify method performance. What's that called? Why would we want to monitor and verify method performance? No, but why do we do that in a clinical lab?
It gives you a small margin of error so that you don't have false positives, false negatives.
Well, yeah, you want to monitor an error because you're running this big equipment, and sometimes that's going to need maintenance. If you monitor and verify method performance, when you can tell when method performance is going downhill, it's time to fix up your machine, right? So that's called quality control. So that's what we'll be getting into after the exam. We'll do our quality control. But now it's just laboratory statistics. So it's also done to interpret the results of clinical laboratory tests. So, and we'll get into that also. So, can anybody tell me what's the difference? So I got it right here. So populations versus samples, right? So population is every person or everything that's in that. It's not a sample, it's the whole group, right?
Well, in my physics class, they said it's impossible to measure.
No, there's populations that you can measure every single one. Like if I could pull out all the lint in my pocket and characterize them based on size or something. Say, that's the whole population of lint in my pocket or something like that. But for the most part in statistics, you're working with samples because it's just representative samples of a population, right? So again, the population is the number of animate creatures or persons or whatever it is you're looking at. And in statistics, refers to a collection of objects, events, procedures, or observations. So samples are representative observations drawn from the populations to make inferences about that population. So we're going to take a sample because for the most part, populations are impractical to get measurements from every single object in a population. So that's why we take samples, and then look at statistics based on those samples and infer something about that population. So, okay? So if the sample's too large, your study might be difficult to carry out, which is why you typically don't look at the whole populations, because that'll be too large. If the sample's too small, the sample may not give you a good representation of the overall population, okay? So here's what you get out the bat. You get a whole set full of data. Do you have this? See? It had changed, I'm sorry.
I just downloaded this from the website, and it's not the same.
The one I just put up? So like I pointed out on the Canvas site, there's a bunch of sections. They all have dates. Do you see it? This Wi-Fi, yes. Not just the Wi-Fi, though. Internet service.
You know what? That's a really good point.
When is he?
Sorry, I know
When
that's
I hear the representative, right? Do you open them out?
I'm not an ambassador. I get no scholarship. You'll find somebody else.
Who's our ambassador?
Sorry. Who's going to hail them?
I should write an email.
I gotta get a hold of them.
Is the president coming this
You're
semester?
so distracted today.
Yeah, I know. What would you do with something like this? What does this tell you?
Throw the TI-83 and get a 5-number summary.
Huh?
Throw the TI-83 and
Get a 5-number summary? But what does that mean? What do you need from this? I mean, before we even do any analysis, we got to know what these numbers are or what they're from, right?
I think
I can infer what they are just based on what the range are and seeing this is a clinical laboratory chemistry class. You got any guesses of what kind of data this is?
Weights and
Huh?
temperature.
Not temperature.
temperature.
Although I can see how there's a 74.
60.8?
What are you talking about?
The temperature of corpses.
I thought you were saying my temperature. Sorry.
No, I'm not saying of a person. I'm saying of like just a thing on a hot plate.
Oh, no, these are clinical lab science, or clinical chemistry lab. So they're probably going to have to be some kind of values from patients. What's it look like?
Oh,
Wait.
blood pressure.
Ooh, that's a good one.
How about fasting glucose?
Oh, yeah. You can do glucose too.
Yeah, I think it's fasting glucose.
Although, I'm surprised not to see a 30 up there.
A 30?
Yeah.
You'd be in a coma, wouldn't you?
No, people have come in and scored 30s on glucose and be alive. But people are often stunned while they're still living.
Yeah.
I've also seen 300s.
So the first thing you need for this kind of data is you need some kind of descriptors, right? So are these from a health fair? Are they the last 100 admissions at a hospital? When's the next one going to come? Oh, it's not. Oh, it came without me touching it. Are they blood donors? Are they 100 selected from the phone book and then had their blood drawn? So it's like, you know, where did they come from? So some kind of descriptor so you know what that data means, right? Next thing you might want to do is kind of sort them low to high. So what's that going to tell you? Range, yeah. So it tells you the range. You sort them from low value to the high value. And then you get to know the maximum and the minimum. So it gives you the range that that's in, right? So then you want to find the three middles. Can anybody tell me the three middles? No. That's two. Mode, yeah. So you guys know what mode is? Yeah, value that occurs most. See, you guys did learn something in your statistics. So Then you're going to want to find the scatter or variation, and that tells you how far. We already found one, basically the range tells you a little bit about the scatter, right, and variation, and then make a graph or two of them. So what or where are the middles? You got the three middles. The mean, which you commonly known as the average, the median, it's the middle point, and the mode, the most frequent value. So which one of these can you have more than one for a data set? Yeah, you could have multimodal data set, and that just means you have multiple modes. So the mean or the average, it's the sum of all the points divided by the number of points. So, and that means the most common measure central tendency, and it's affected by extremes, right? So if we have one outlier, it's going to skew that mean one way or the other. Whereas the mode and the median aren't affected by
When you
extremes.
do the mean of the population group, don't you exclude outliers?
Say again. Well, you can't just say that one's high. There's like a test that you do.
Well, yeah, okay.
So, and effect of the, and this shows you just as an example the mean for different data sets where all the numbers are basically identical except for this the largest number, the max, and it goes up from 88 to 98, 108, 118 to 128, which shifts the mean from 79 to 82. So, and that's what I just showed you. I don't know why it's on there. But one thing to note is that the median's not altered by that, right? So the median's always going to be the middle point. In this example, it's 69. And what's the mode in this set? Can you guys see?
67.
Yeah, 67. And that stays the same also for these. So, and this isn't that data set, but this shows you the mode here. It's the number that's more common out of all the data sets. And it's the value that occurs most often. The distribution may have more modes. This example is bimodal, so you have 64 and 71. And then this is the figure from your book showing you the three: mode, median, and mean. So this is for a non-normal distribution. Do you guys remember that term? Gaussian distributions. And this is a bimodal distribution. So you got your primary mode here and then a secondary mode over here. So for a Gaussian distribution, how would this look? Gaussian distribution, you're going to see your mode, median, and mean all overlapping basically with equal distributions around that. So the mode 2, value that occurs most often in a data set, and it's not affected by extremes also, and it's not necessarily the middle, right? So measures the scatter. So we have minimum and the maximum in this set. One measure of scatter is just setting the range. Another is the range. You know, it's going to be your high subtracted from your low. So you got, in this data set, our range is, what, 75, 39 minus 104, so 75. Or you can combine them like this, range 75, and then have the whole range outlined there. And you guys already know the low term is the minimum, and the high term is the maximum. So now we're going to get to quartiles. You like quartiles, I keep hearing about them. So you can divide the data set into fourths, and that makes them quartiles. Quartiles 1 and 3 are the most common, Q1 and Q3. And the range between Q1 and Q3 represents the middle 50% of the data, right? And have you guys seen those box and whisker plots? So this shows you the box and whisker plots where you have, this is your first quartile, second quartile with your median, third quartile, and then fourth quartile. Gives you like a visual representation of the scatter of the data or the range of the data. And then descriptive statistics for this data set would include your mean, your minimum, your maximum, the range, the median, quartile 1 and quartile 2, or 3 rather. And also the number of data points that are in. Have you guys ever heard of a scatter plot? Okay. So it looks something like this, where you have all the data points plotted based on what number they are in the data set, and then scattered around the mean, right? Gives you an idea of the scatter. A variation of that is the difference plot, where it's the difference of each data point from the mean. So of course the center line will be 0, and then you get the data scattered around that. So these are the type of plots that you'll see in quality control, very similar to this anyways. Can you see, like, let's look at this middle part of the data. If we saw this, as far as our quality control goes, do you think this would be an issue? Like there could be something wrong with the machine? You see all those data points, they're all below the mean successfully. So that could be like a shift in our machine, maybe due to battery agents, or you need to clean some kind of electrode or something because we're not getting the values that we should. Or you got a trend going up in the last section, right? So things like that. So a difference plot, or you can have a percent difference plot, basically, which is very similar. It's, instead of the actual difference, it's the percent difference from the means. So, have you guys drawn histograms before? Good. So we get a histogram, you know, you have different bins that you can adjust the size of the bins, and then the number of values that are in those bins. And then you get an idea of the population distribution that way. And they say the number of those in the bins is the frequency, right? So they call these frequency distributions. If you have too many intervals or too few intervals or bins, it may give misleading idea of the distribution of the data of the histogram, right? So if you have too few, you'll just have like maybe one value for each value, right? And it's just going to look like a big flat area. Too many, you just might have just one big bar, maybe with a couple on the outside or whatever. So you don't get a good idea of the distribution. So here's some descriptive data of 100 points on the next slide. There are 4 histograms where the number of bins has changed. So you have N of 100, the mean is 72, the minimum is 25.6, the median 72.6, maximum 138.4, and your mode is 72.6. So these are all, your 3 means are all pretty much overlapping. Not quite, but pretty much. You guys know what skewness is? You can tell this is pretty close to 0. So when you have 0 skewness, that means basically you're Gaussian, or you're close to being Gaussian distributed. So your mean, median, and mode are pretty much going to be overlapping, which they're almost doing here. And that's why your skewness is so low. Kurtosis, right? That tells you how pointy it is, basically. So these are your histograms. So you have 3 bins, increasing to 4 bins, to 6 bins, to 7 bins. So which one of those do you think best shows the data? Yeah, probably 6 or 7 bins, right? So does it look symmetrically distributed, basically? For the most part. Which it should, because your skewness is pretty low. Your mean, median, and mode are all pretty much the same. Not quite, but almost. So the shape of a histogram, it could be pointy or flat, right? And those aren't the terms they use in statistics, though, so they're going to use... Huh? Sure, but we're going to use kurtosis, I think. Or for the skewness, histogram could be skewed. Here it's positively skewed because you have a couple outliers that are really big, right? And then this is negatively skewed, so you have a couple outliers that are really small. So to the right it's positive, to the left negative. 2 statistics to measure the shape of a histogram. That's your kurtosis, which tells you if the shape is pointy or flat, or the skewness, which moves it positive or negative, depending on whether it's negatively or positively skewed. So another measure of scatter is the standard deviation. Can somebody just give me, what do you think of when you think of standard deviation? What do you think it is a measure of?
The average distance between the points.
The what?
The average distance and the relationship between the points.
So it's almost, it's like almost the mean of the average, it's like the average distance from each point to the mean, right? But if you actually calculated the real average, you'd end up with 0. Do you know why? So, because if you're going, so you have, let's say, 3, 5, 7, 8, 10, 11. So let's say that's our data point. What's the mean of that? 3 plus 8, 18, 16, 26, 37 plus 7, 44. So it's 44 divided by, what's that, 1, 2, 3, 4, 5, 6. What's 44 divided by 6? So this is X bar.
7 plus 3. 7 plus 3.
7.3 or 2?
7 plus 3,
7.333. Okay, so that's the mean. So now if we want to calculate, if we were going to take the average from the mean, so it would be 7.3, 3 minus 7.3, 3 minus, 5 minus 7.3, 7, and these are all added up, right? The differences, 7 minus 7.3, and so forth. We're going to get a number of negative values and a number of positive, and they'll actually sum to 0 because that's basically how we calculated the mean, right? We calculated them up and divided it by the number, which this should all be divided by 6. So if we calculated the difference from the mean, it would end up at 0. So that's not a good way to calculate the standard deviation, but that's where you get this from. If you square all of these, you get rid of all the negative numbers, right? So then we can basically get a measure of how far things away are from the mean. And then divide it by the total number of the population. Although, you notice this is n minus 1. Why do you think this is n minus 1 if we're, have all the data points? Because this is actually, what we're doing here is another standard deviation calculation, and you'll see it in Excel. But we don't want to use this one unless, anybody got any ideas when you would use this one rather than this one? The same thing as this, but without the n minus 1. Remember at the beginning of the lecture we talked about the difference between populations and samples. So this is the standard deviation of a sample. Because we don't have all the data points, it's like if we actually did it divided by n, it's just an estimate of the standard deviation, so it's not the actual standard deviation. If we had all the values from the whole population, we know that would be the standard deviation without the n minus 1. So the n minus 1 makes this a little smaller on the bottom, which makes your standard deviation a little bigger, so you're a little less precise. Does that make sense? It's because it's just an estimate. So this is the equation for standard deviation of a sample. So we include the n minus 1. And this value, I was just showing you, how that standard deviation works. So it's almost like the average difference from each point from the means. But we got to have the squares in here to take care of the negatives, and it also gives a little bit of weight to large numbers, right? So it makes that effect very, a little bit bigger. And then you take the square root of everything, kind of normalizes everything again. So standard deviation in the Gaussian curve. So here's some numbers you're going to need to know on your test, right? So you've heard of this, so here's your mean. Plus or minus 1 standard deviation is going to represent about 68% of all the data points. Plus or minus 2 is about 95%, and then plus or minus 3 standard deviations represents 99.7% of all the data points in your sample. Do you guys remember that? So yeah, remember that again. And this is another standard deviation. It's a little bit different. If you notice, this one, standard deviation's 8. This one, standard deviation's 4. And again, 1 SD, 2 SD, and 3 SD. It doesn't matter your standard deviation. The standard deviation, you're always going to have that proportion of the population under those standard deviations. So Gaussian histograms with n equals 30, 70, 11, and 150. So we'll see what that looks like. So which one do you think looks normal or Gaussian? As you increase in the n, right, it starts to look more and more Gaussian. Does that make sense? So you may have a lot of times, like when I'm doing science, you'll have a small sample set, or stuff you get from the lab, you'll have a small sample and it won't look Gaussian, but if you kept increasing numbers, eventually it might look Gaussian, but not always, but for the most part, probably look Gaussian. Anybody know what the coefficient of variation is? And why would it be important in a lab type setting? So basically, it's a measure of relative precision, right? So percent CV, you have your standard deviation times 100 divided by the mean. So percent CV is important, especially in a lab setting. If you have two different techniques that might have two different, if you have two different, units, measures of unit, this can tell you which one. You can compare the variability between both using this because there's no units in percent CV. Your standard deviation is going to have the same unit as your individual values, and so will the mean. And with this equation, the standard deviation and the mean, the percent CV becomes unitless, right? Because we lose that unit in that little equation. So if you're going to want to compare variability for two different methods that happen to have two different units, you want to use the percent CV. There's no units involved in that. And you can see also percent CV, like these have equal percent CVs, but if you look at the standard deviation, this one's 9, this one's 1.5. So, but they're equally as precise, right? Whereas you could have here, we have equally sized groups with different standard deviations, which results in different percent CVs, right? So those, which one's more precise there? Which method? Yeah, this one, right? It's got the lower percent CV. Anybody know what the Z-score is?
No.
Yeah, so you calculate the Z-score basically. You know your standard deviation. You have one data point. You want to know the Z-score. That's basically how many standard deviations away from the mean that point is. And you will use that when we start doing quality control charts. It's all based on number of standard deviations away from the mean and how the points fall on that. So also the z-score, you might see it as the standard score, the normalized score, or the SDI. You guys know what QAP? Quality assurance programs, I think. So you might see it named as all these other things, but it's just the z-score. So you have your single value subtracted from the mean and then divided by the standard deviation. Yes?
We're going to use a z-score sheet.
A z-score sheet?
So like, front back from negative and positive z-scores and percentages.
No, you can calculate the z-score.
Yeah, but it's really like percentages, like where you're at.
You just need to know those critical ones, the 1, 2, and 3 standard deviations or z-scores. Yeah. So there might be some questions where you have to calculate the z-score, because when you do quality control, you got to calculate the z-score and then plot it on one of those like percent different. It's similar to those percent different plots where you have the mean in the middle, and then instead of on the vertical axis, instead of values or the difference from the mean or percent difference, it's going to be the z-score basically. Standard deviations away from the mean. And then there's this whole set of rules that goes with where they fall in consecutive data points, how they fall, whether you have an issue you have to take care of or not. So we'll go over, there's some of those questions I think you have to calculate the z-score in that method. So it's an example of an SDI. So this group, my November mean's 212, the group mean, so this is for that, like cap will come, I'll give you a group mean, tell you what your mean is. And in this group, the group mean is 214, standard deviation is 8.6. So we want to figure out how far away from the mean we are, because you fail those proficiency testing if you're so many standard deviations away. And ours is 212 minus 214 divided by 8.6, so we get negative 0.23. So that's pretty average, right? So we're right there near the mean. So with this z-score, we wouldn't have to worry about failing the proficiency test. So what about confidence intervals? They're kind of related to z-scores, right? So 95% plus or minus 2 standard deviations, so you'd give the mean, and then plus or minus 2 standard deviations, that'd be your 95% confidence interval. And what does that mean, 95% confidence interval? Yeah, right, so that, exactly. So we're 95% of the time, the data point will be within that range. 99% is going to be 3 SD, or 99.7% rather. So 99.7% of the time, you'll be within that confidence interval when you take a data point. So. Anybody ever heard of the standard error or standard deviation of the mean? This I don't think you use so much in a clinical lab, but you'll see it all the time in scientific literature. The standard error of the mean. And basically it's your standard deviation divided by the square root of the sample. So, and what does that do? Why would people want to include that in like scientific papers? They always make their bar graphs based on standard error of the mean rather than standard deviation. And the reason is it makes those error bars look smaller. Okay. So the true mean, we talked about this a little, the true mean related to the sample mean. So, and the true mean is going to equal the sample mean plus or minus the t statistic times the standard deviation. And the t value is obtained from a t-table and depends on the degrees of freedom. Right? Did you guys do t-tables? Look at t-tables? Yeah. So we'll do some of that. I'll include a t-table on the test so you can look it up. Huh? Yeah. And what do they mean by the desired probability? You've heard of p-values? Most common p-value is 0.05. You can also see 0.01, 0.001, or 0.1. So when you're doing t-tests, they use these different p-values. It's basically the probability. Well, but I don't know how to explain it. I know how to explain it in terms of t-test. So do you guys know what t-tests are for?
Check for differences between two experimental means of an experimental mean and a stated value.
Yeah. So, and the p-value, when you say something's 0.0, so yeah, we haven't gotten into the null hypothesis either. You got, what's the null hypothesis when you do a t-test? So the null hypothesis is that both means are the same. So with the p-values, the probability, when you have a 0.05 or smaller, that's the probability that those two means are the same, 0.05. So that's 5% chance that the two means are the same based on the data that you've tested with the t-test, which is a pretty small chance. So typically, your p-value on your calculated t-statistic needs to be smaller than 0.05 to be significant. You got to, when you're doing a test like that, you define what the significance level is going to be. Typically, it's 0.05. Some cases it would be 0.01, and less rigorous cases, 0.1. But before you actually set out to do the test, you're supposed to define it beforehand. So that'd be like the probability that the two are the same. If with a 0.05 p-value is 5%, which is a pretty small percent. So a lot of people say, oh, that 5% that they're the same. Chances are they're not the same, right? So, so accuracy and precision. You guys know this. Accuracy basically describes the ability of an analytical method to obtain the true, correct result after a number of replicate analyses are performed. So accuracy, you can like hit the target right on, right? Precision describes the reproducibility of the method, so that's your scatter, right? The narrower the distribution of the results, the smaller the standard deviation, the better the precision. So small scatter, better precision. On the target, you have good accuracy. And that'll go into, in the clinical lab, you have methods that are trying to test, measure different values. So you can have accuracy there, and then your standard deviation around those true values is precision. You know what the difference between the true value and the mean measured value is? What's that called? That's going to be the bias in your measurement. One semester, somebody didn't like me using the term bias, saying but that's, yeah, that's okay. I kept using it. So, this is a figure from your book. What is this figure showing you think? Yeah, standard deviations are getting smaller. So, group 1 is more precise, and then you lose precision as you go. Group 2 is a little less precise, so it's wider, and then group 3 is even less precise, so yeah, it's a lot flatter. So just showing you difference with precision. And this shows you, you know, bias data, or actual difference between two means, right, where the means aren't equal. Which could be represented between like these, because that last group looked like it had relatively the same precision, but different accuracy. So, and this is the figure from your book. What does this represent? Good accuracy, but poor precision. Good precision, but poor accuracy, and this is like good accuracy and precision. So, I always get these two confused too in my head. I got to sit there and think about it. Accuracy, precision. Accuracy is on target, precision is the scatter. So try to remember that. So the null hypothesis, this is where we were a few minutes ago. I'm scattered today. I got poor precision, right? So, but I'm accurate?
I said, but how did you?
Yeah, that's a good question. Probably pretty poor also. So when comparing two samples from two populations, the differences between the means and the S will be observed. So you'll see different means and different standard deviations. Differences may or may not reflect the true differences. Like you can get differences in the means and differences in the standard deviation, but it still just may be sampling, you know, just variation in your sampling, right? So they still might reflect one true population, or they might reflect two different populations. So to test whether their two means are equal, you use a null hypothesis. And the null hypothesis is there's no difference between the true mean or the true standard deviation. So we're saying that they're the same. And we got to look things up on the t-table. You have to know the degrees of freedom. And that's defined as the number of ways in which a group of numbers can vary independently, right? So if we have a data set, a lot of times you see it as n minus 1, and that's because we've got the data set, and it's got all the population there, but we've got one estimate there, and that's the mean, right? It's calculated by subtracting the number of estimated parameters by the sample size. So estimated the mean, and then you have the sample size. So n minus 1 typically. So the F test, this is a test that's done to see if there's any differences in the variances, right? So, and it's calculated, you divide the larger variance. I didn't define variance, did I? What's the variance? Can somebody tell me? How's the variance related to standard deviation? It's just, it's right here. If standard deviation is S, the variance is S squared. So it's just the square of the standard deviation. That's your variance. Okay? And the F test, you take the larger variance, divide it by the smaller variance, and that gives you your F statistic. And then you look up on an F table, and based on from the F table, based on your degrees of freedom and the p-value that you've selected, you can determine whether the variances are different. And this is important to do before you're going to do a t-test, because t-test assumes that the variances are equal. Okay? So the t-test is used to check for differences between two experimental means or between an experimental mean and a stated value. And testing the difference between an experimental mean and stated value or known mean involves testing to see if the stated value is included in the confidence interval around the experimental mean, basically. So that's what a p of 0.05 would give you a 95% confidence interval around that stated mean. So it's t equals your calculated mean divided by that stated value or true mean, and then the standard deviation divided by the square root of the n. So that's how you calculate the t for that case. Then you have an unpaired test, and that's when you're comparing the difference between means of two independent populations being analyzed. So we calculated the height between all the males and females as two independent populations. We do the F test first to make sure the variances are equal, and then we can compare to see if we're significantly different in height between males and females. Using an unpaired t-test, and that's if there is no difference in the variances calculated in the pooled samples. So this is the variance of the pooled samples. You got to calculate the t statistic, which is the difference between the means divided by the pooled standard deviation times the square root of 1 divided by n1 plus 1 divided n2. And then the critical t-value is found on the t-table based on the p-value selected again, and you can see if the two are different. So. So then we have a paired t-test. So this is basically what you get from repeated measures, right? Finding an experimental effect in a single group before and after, that's like an example of repeated measures. Creating a new distribution, reduces sampling error, it's more powerful than a regular t-test, and it has limited applicability, right? So you can do these before, after, it doesn't necessarily have to be before or after. You can like measure, you know, here or here. So it's not necessarily before or after. There's a number of different ways to do repeated measures. But basically, you get 2 data points from one subject, and then you're going to compare, is there differences between this state and this state overall? And you do that with a whole sample. So for a given study, 2 groups of subjects could be closely matched in age, IQ, blood pressure, income, or education level. And you get data like this. So this is the individual subjects. This is state 1, and this would be state 2. Looks like this guy goes from 2 to 6. This guy goes from 13 to 17. This guy goes from 24 to 28. If you were going to do a regular t-test, you would average those, right? And then see, are these groups different, basically? And you're going to have, in these data sets, you'll have pretty big standard deviations, right? So is 13 different than 17, or 13 minus 17 different than 0? That's your null hypothesis says 13 minus 7 is going to be 0, right? But these standard deviations are going to be pretty big, so your test isn't going to be so powerful, right? So, but that's where repeated measures tests comes in. You look at the difference within one subject, and if you look, they're all 4. And that's your new variable is the difference, right? D. And is 4 different than 0? So that's the new test that you're going to be looking at. So looks like the variability here is nothing. Because there's no variability, everyone's got 4. So basically, you're more likely to detect differences because you cut out a lot of the error, the inter-individual error. So you're only looking at, the effect of before and after, or whatever states you guys are collecting the data in. So the fundamental advantage is the error term in the within subject design is smaller. Simplified example, the standard error terms would be higher in the 2-sample version versus the difference test, right? Because 4 minus 4 is 0, basically. The advantage is that the individual differences are not part of the error. So it's just the differences between this state and this state, right? And I don't think there was a 5. So paired t statistic is you get this. So it's t minus x bar 1 minus x bar 2 divided by the standard deviation divided by the square root of the sample size. So have you guys you guys didn't see ANOVAs in your last stats class, did you? So ANOVA is short for analysis of variance. And it's used when 3 or more groups to test if there's differences amongst those means, but 3 or more groups. So you could have, like, for this example, we have caffeine study with 3 groups, no caffeine, a small dose of caffeine or a big, like, Jolt Cola dose. Level is the value, kind or amount of IV. Treatment group is people who get specific treatment or level of treatment. Treatment effect is the size of the difference in the means. So have you guys ever seen studies where they have different doses and you're looking for effects, basically, of those different doses? So with multiple groups like that, you have to do an ANOVA, or analysis of variance. So we have 3 means to test. And the null hypothesis is that all the means are the same, basically. So you could take them 2 at a time, but really you want to test all 3 more at once, right? Do you know why you wouldn't just do multiple t-tests? So remember that t-test, you're selecting a probability that and typically it's a 5% probability that they're, going to be the same as where you say that they're not the same. So if you do one, if you're comparing these 2 groups, so that probability is 5% that they're not the same, so you selected that they're different, and then you're going to test this one and this one. You're doing that probability again, you multiply those probabilities, so it goes from 0.05 times 0.05 equals 0.025. So it makes it harder and harder to really detect differences because the probability multiplies. 0.05 times 0.05 equals 0.025. And if you multiply that again, 0.05 times 0.025, it's going to be 0.00, or wait, 0.05 times 0.05 isn't 0.025, is it? So that's 1, 2, 3, 4. 0.0025, right? So, and then it keeps getting, harder and harder, basically, because those probabilities multiply. So, but anyways, the rationale for so you have to check them all at one time so you don't get that multiplication of probabilities. Instead of using a mean difference, we can use the variance of the group means. So you look at the group means and take the variance between those means, right? And you take the variance of the group means about a grand mean over all the groups. And the logic is basically the same for the t-test. You compare the observed variance among means, observed difference in the means in the t-test, to what you would expect to get by chance. And this is an example. So you have these 3 groups. These 3 means are all pretty similar. And based on looking at the variance from these, you could probably assume that these 3 means are going to be the same. The null hypothesis will prove to be true with this. So these are 3 samples from the same population. That's what the data looks like. Whereas these are 3 samples from different populations. You'll get group, mean 1, mean 2, mean 3, and then your group standard deviation. So your overall mean is going to be somewhere, but then based on the standard deviations, you can assume that these groups are going to be different, right? So I'm not going to actually have you physically calculate ANOVAs by hand because that's just a pain, and really, yeah, just to understand what it means and how they're done. Typically, you use just statistical software to perform them these days because it's a heavily involved hand calculation to do them. So I'll just have you do the t-test, okay? Huh? Oh, it's even easier in Excel, and I'll show you how to do it in Excel because you'll have to do some of that for your laboratories. Yeah, I think it is really easy to do in a TI-83, but I forget how to do it. Because you got to do those lists and things, right? Yeah. I haven't done that since I took stats at Santa Fe. But Excel does it really easy too. And I'll show you guys how to do that. But on the exam, I was going to have you look up the T table, the T statistics. So suppose we complete a study and find the following results. Either graph, how would we know to decide whether it's a real effect or not? And to decide, you're basically going to compare the observed variance in means to what you'd expect on the basis of chance given the true difference in the means. So, and that's basically the same as a t-test, but with multiple groups. But remember, you're looking at the group means and the group mean variance. So we were talking about outliers. That's a gap test that you test for the outliers, and it justifies the exclusion of a data point deemed to be an outlier. So you have to do that. And then next time we'll talk about non-parametric distribution statistics. So we can go ahead and do that lab real quick. You want to do it in here, next door?
I thought it was really cold.
Oh, so you want to be in there? Oh. Because it's hot in here. So I'm going to get...